Today we will discuss relativistic electron beam plasma interaction, extending our work that we did earlier on non-relativistic electron beam plasma interaction. Well, delving into the problem of relativistic electron beam plasma interaction, I will make a few remarks on non-relativistic true stream instability, and then I will go over to discuss the response of relativistic electron beam to an electrostatic wave or a plasma wave. We will reduce a dispersion relation and obtain the growth rate, and then we will cite some practical applications of this study. Well, the reference for today's presentation is this book, Interaction of Electromagnetic Waves with Electron Beams in Plasmas, by Professor C.S. Liu and myself. Let me begin with the remarks on two stream instability. This we studied earlier. For a non-relativistic electron beam, we considered that if there is a plasma through which an electron beam is launched, then it gives rise to generation of waves in the plasma. The wave in the plasma, we called it as a plasma wave with a potential phi, we wrote down as some a exponential minus I omega t minus k z, and the beam had a initial velocity v0 b along z direction. As a consequence of the interaction of the beam with the plasma, we found that the frequency of this mode omega was expressible as omega p, the plasma frequency of electrons of the plasma, plus a quantity delta, which was also equal to k v0 b plus delta, and delta we obtained. The value of delta that we obtained is equal to omega p b square, the beam plasma frequency square, into plasma frequency of the plasma electrons divided by 2 raised to the power 1/3, and for the unstable mode this was minus half plus I root 3 by 2. I can call this quantity as real part of delta plus imaginary part of delta, that I called as gamma. But if you look at this expression, delta r is simply equal to gamma upon root 3. This term is root 3 times bigger than this one. So we find, and this is negative time. What is the consequence of this? The consequence of this is that the omega that I had written is equal to k v0 b plus delta. So if I write down the real part of frequency, it should be equal to delta r. But because delta r is negative, you may note here that if I calculate the quantity omega r upon k, it is equal to v0 b minus gamma upon root 3 k. So this is less than the beam velocity. The ratio of real part of frequency to wave number is called phase velocity of the wave. So phase velocity of the wave is less than v0 b for the unstable plasma wave. The wave whose amplitude grows with time must necessarily have a phase velocity less than v0 b, and this is the same condition that we deduced physically for charge bunching. So this condition essentially ensures that the electrons are bunched in retarding phases of the wave. Now with this, the amplitude of the wave will grow. So what happens, that phi now appears like a e to the power gamma t exponential minus I omega r t minus kz. This is the growth in the wave amplitude with time. The question arises, how long this amplitude will continue to grow? After all, when a plasma generates a wave of growing amplitude is so much now, then it becomes larger and larger. So when the wave has acquired substantial amplitude, then obviously the electron beam may get trapped inside the wave. These are the potential energy minima. So what can happen, that when the electron can be trapped in this wave, then it will bounce back and forth, and it will no longer give energy to the wave. So the instability will stop when the wave has acquired large amplitude and the electrons are trapped, beam electrons are trapped in the potential energy minima of the potential of the wave. Now, in order to understand the trapping of particles, we can do one thing. Let us write down the equation of motion. The equation of motion is m d, for a single particle I am writing, so d2z by dt square, this is acceleration, is equal to the electrical force due to the wave on the beam electron, which is equal to E grad phi, and grad phi is simply I k into phi, which is a exponential minus I omega t minus kz. I am examining the behavior of the electron in some sort of a steady state when the amplitude of the wave is no longer growing, and I want to find out how the electrons behave in the potential energy minima of the wave. So in order to understand this, let me write down the actual force on the electron is the real part of this expression. So it becomes E k a, and I can write down this as sine omega t minus kz. If I multiply this equation now by dz by dt, so this is m is already there, d2z by dt square is there. I am multiplying both sides of this equation by dz by dt and dt and integrate on time. This first term gives you d dt of how much you get? You will get dz by dt whole square, dz by dt whole square into m by 2. I think I made an error. This integration is tough because t is involved in there. So first of all, I must get rid of this. So I think I must do something else before I multiply this. I will do the following. I introduce a new variable z prime, which is the coordinate of any point in a moving frame, moving with the velocity of the wave. So let me call this quantity z prime is equal to z plus omega upon k into t. Let me introduce a new variable. When I substitute this in that equation, my equation becomes m d2 z prime dt square is equal to E k a sine k z prime, and with a negative sign here. This is the equation that I get. Now this equation can be integrated because there is no explicit time dependence on the right hand side. So just by making a transformation from z to z prime given by this expression, my equation of motion for the electron of the beam in the presence of an electrostatic wave becomes so much. Now multiply this equation by twice, or rather dz prime by dt, and integrate. This 2 is not required, you can delete this, multiply this and integrate. This equation essentially becomes dz prime by dt whole square into m by 2 is equal to minus e k a. Now when you integrate sin kz prime, it gives you k here and becomes cos function of kz prime and plus a constant here, constant of integration C1. This equation has a simple interpretation. This is the velocity of electron in the moving frame. So half mv square is the kinetic energy of the electron in the frame moving with velocity omega by k, the phase velocity of the wave. This is the potential energy because a cos phi cos kz prime is the potential of the wave. So k obviously will cancel out and this becomes the potential energy when you take on the left hand side. So this can be written as kinetic energy means half m vz prime square plus potential energy, which is negative of this quantity, is equal to constant, which means that if I plot potential energy, let me write down potential energy. Potential energy is minus E A cos kz prime, and if I plot this quantity as a function of z prime, potential energy plotted here, then this quantity will be like this. So there are regions of minima, and this is where the potential energy is minimum. What will happen? As the wave amplitude grows with time initially, then this amplitude well, this potential energy well will increase. So that height from here to here, this will increase with time, and it is possible that in the moving frame the electron velocity is how much? So in the moving frame, beam electron velocity is V0b minus omega by k. This is the velocity. Whenever, so what is the kinetic energy? This is half m and this quantity is square. So this is the kinetic energy of the electron in the moving frame. Whenever the difference in potential energy from here to here becomes of this order, the electron will be totally trapped. So the condition for trapping is when this becomes of the order of EA, of that order, maybe you can put 2 EA from bottom to top typically. So when this is of this order, the electron will be trapped in the potential energy minima of the plasma wave, and this gives the amplitude of the plasma wave. So if you want to calculate the amplitude of the plasma wave, this is the condition, and this is called saturation amplitude of the plasma wave. And what you can do, omega by k we already obtained in terms of, because we just wrote down omega is equal to, this is the phase velocity, so actually it's omega r by k. So, omega r by k we just calculate was this quantity was omega p or k v0b minus gamma upon root 3. This is what we had seen. So, use this value of omega in this expression, then you can get the value of A, the amplitude of the plasma wave, and the result turns out to be, let me write the result. It turns out to be E A upon half m v0b square. This is the potential energy of an electron, maximum potential energy of an electron, divided by the initial energy of the kinetic energy of the electron beam. This becomes is equal to gamma upon omega p root 3. And if I put the value of growth rate gamma, it turns out to be beam density upon 2 times the electron density to the power 1/3 into 1 upon root 3. In most of the experiments, beam density is a few percent of electron density, and this quantity could be of the order of greater than around 0.1. So, if you are launching an electron beam of say kinetic energy of the order of 1 kilo electron volt, then the amplitude of the wave would be of the order of about 100 volt per 100 volt. Potential amplitude will be about 100 volt. So, you are really generating a very large amplitude plasma wave by this method. So, an electron beam can very easily generate a plasma wave in a plasma, and the plasma wave can acquire large amplitude. So, what will happen in the potential energy minima? The electrons will look like trapped, like they are going back and forth. So, they are no longer transferring the energy to the wave. On an average, they will stop giving energy to the wave, and wave growth stops. But has been experimentally observed that if you plot the amplitude of the plasma wave as a function of time, then initially the amplitude was very low, and the wave amplitude actually oscillates like this and then acquires a constant value like this. This is a commonly observed feature of a true stream instability. Here I have ignored the effects of plasma magnetic field on the plasma. Now, I would like to see what will happen if the beam velocity was relativistic, if the initial beam velocity v0b was of the order of c. So, I am studying the response of a relativistic electron beam to a plasma wave. Well, geometry is very similar, but the electron gun that you have to employ for this purpose is essentially a gun which can produce large velocity electrons, and a very special kind of gun is usually made for this purpose. As I mentioned yesterday, this is a gun which has a cold cathode with a knife edge, circular knife edge, and that emits electrons. Usually the beam that you produce here is annular electron beam. There are ways you can produce a solid electron beam also, but the effects of finite size of the beam or of the structure of the beam I will not consider at the moment, though we can easily include those effects. They are called non-local effects. So, today I will just consider a ideal situation. So, this is actually a field emission diode, this is cathode, this is anode, and an electron beam is coming out, and we have a plasma somewhere and it's passing through the plasma, and I want to examine the excitation of a wave in the plasma, longitudinal electrostatic wave in the plasma in the presence of the beam. One thing you can easily see here, that the wave generation occurs due to Cherenkov resonance. Which means that omega has to be equal to k dot beam velocity. This condition turns out to be valid even in a relativistic case. So, what happens when V0b increases, k must decrease to produce a given omega. And as before we have seen, we had as earlier we had seen that the frequency of the most unstable mode is of the order of omega p. So, if frequency is fixed by the plasma density, then the k of the wave is fixed by the beam velocity. So, the phase velocity of the wave has to be close to beam velocity, and hence k will decrease with increasing beam velocity. In last few years, a lot of experiments have been done with electron beams which travel with velocities close to 0.9 c, 0.95 c, 0.99 c, and they found generation of very large amplitude plasma waves that can be used to accelerate the particles. And we shall discuss this as an application after I have discussed the effect of relativistic mass dependence of electrons on two-stream instability. Well, the equation of motion in this case is modified, which says that dp by dt, if this is the momentum of an electron, by dt is equal to the force, which is minus E into E. I forget the collisions, I forget the magnetic field, I forget the pressure term for the electron beam response. So, I want to solve this equation. As I mentioned before, total time derivative of momentum can be written as partial time derivative of momentum of the electron fluid. This is the average momentum of electron fluid plus V dot del P is equal to minus E. This equation we have to solve, where momentum I can write down as mass of the electron into velocity of the electron into Lorentz factor gamma, and gamma is related to V as gamma is equal to 1 upon under root of 1 minus V square by C square to the power half. This is the Lorentz factor. So, the fluid equation is now modified by the introduction of a term called relativistic gamma factor, and because I am solving this equation for beam electrons, I will put a subscript b on these quantities. So, particle velocity is b, gamma b I will write down. So, gamma b is beam velocity square like this. Here also this equation I have written for beam. So, I will put a subscript b here. Well, in order to solve this equation and the equation of continuity, first of all we have to identify the equilibrium, and then we perturb the equilibrium by the plasma wave field. So, now what is our equilibrium? Our equilibrium is initially we have electron density of the beam is equal to n0b, and beam velocity is Vb is equal to V0b, and that is in the z direction. This is my equilibrium. Now I perturb this by a plasma wave. The potential of the plasma wave I will take as a e to the power minus I omega t minus kz as before. Then we say that in the presence of this plasma wave, my beam density has changed from n0b by an amount n1b, and velocity has changed from v0b z cap to a quantity called v1z in z direction, because the potential I have chosen so like this. So if you take the gradient of phi, then the electric field will be in the only z direction. So we expect that the particle will gain velocity or lose velocity in the z direction, because particle motion is influenced only in the z direction. You can verify this. What you have to do, we have to substitute these in the equation of motion continuity and linearize the equation of motion. So linearization is a very important step. Well, the quantity that I get there is a quantity gamma v. So let us see how this looks. This is equal to the product of, well, gamma depends on velocity, which is vb0 plus vb v1 bz. This is the gamma is a function of this quantity multiplied by v0 b, the initial velocity, plus v1 bz, this is the velocity modified. So this is the value of this quantity. What I can do, gamma I can expand like this. So gamma at vb0 plus v1bz, because gamma actually is a function of, so anyway you can write down this by Taylor expansion, gamma at vb0 plus delta gamma upon delta vb at vb0 into v1bz. Simple. And the expression for gamma that I had given to you, if you differentiate, this turns out to be simply, I will call this quantity as gamma 0, the initial value of Lagrange factor, plus this turns out to be gamma 0 cube into v1 b z into v0 b upon c square. You can just verify this. Just differentiate gamma with respect to beam velocity and replace this beam velocity by b0 b, and this is what you get. What is gamma 0? Gamma 0 is equal to 1 minus v0 b square by c square, the initial value of gamma factor, and gamma 0 cube is the cube of this quantity. You can easily verify by differentiating. And when we substitute this in that expansion, then what my gamma v becomes? Let us see. Gamma into v for the beam, I am writing, it becomes gamma 0 v0 z, well, v0 b, plus you will get a term which is gamma 0 into v1 bz, plus you will get a term gamma 0 cube v1 bz v0 b square by c square. All these quantities are in the z direction. You can combine these two terms by taking gamma 0 cube common, and this becomes z cap, I will write here, First term is gamma 0 V0b plus gamma 0 cube common. Take V1b also common. Then you are left with gamma 0 square minus square inverse plus V0b square by c square. This quantity you can write down as, by this expression, 1 minus V0b square by c square. This will cancel with this, so this becomes unity. And consequently, and here I have ignored the product of V1b with V1b, square terms I have ignored on linearization. So this becomes simply z gamma 0 V0b plus gamma 0 cube V1bz. And when you substitute this in the equation of motion and linearize, what do you get? Let me write down this in the equation of motion. The equation of motion was m outside delta delta t of gamma v. Gamma v means the first term that I had written, gamma 0 V0b, does not depend on time, so I will not write it. You will get gamma 0 cube V1bz. The second term is V0b delta delta z of this quantity gamma 0 cube V1bz, because gamma 0 V0 term, when you differentiate by z, is 0 identically. So this is the only linearized term that that survives. And right hand side was the electrical force, which is E I k multiplied by phi. Once you have obtained the linearized equation of motion, you can replace delta delta t by minus I omega and delta delta z as I k, as we have been doing, and you will obtain from here V1bz is equal to E k phi with a negative sign into m omega minus k V0b. This is V0z or V0b, actually the same thing, multiplied by gamma 0 cube. An important noteworthy change brought in by the relativistic effect is the appearance of this gamma 0 cube. If the beam was non-relativistic, then this term will not be there. As a layman, one would think that relativistic effect essentially modify the mass. M is the rest mass of the electron. So one would expect that this should be m into gamma 0. But in electrostatic response, it's the gamma 0 cube that comes in. So when you do a proper linearization of the equation of motion, the effective mass of the electron due to relativistic effect is not m gamma, m is replaced by m gamma, but is replaced by m gamma cube. This is the important modification. Please understand what is the magnitude of gamma 0. For an electron having energy equal to rest mass energy of an electron is about half MeV. So if you have an electron with energy, kinetic energy of half MeV, so total value of energy is rest mass energy plus kinetic energy is 1 MeV. So this half MeV kinetic energy electron will have gamma 0 equal to 2. So then gamma 0 is 2, but the gamma 0 cube is 8. So effective mass as far as the response of electron to the wave is concerned is suppressed by gamma 0 cube, means 8 times. This is a very important reduction factor. And then we solve the equation of continuity, which is for the perturbed density turns out to be n delta n1b upon delta t plus divergence of N0b into V1b plus N1b into V0b. This is the equation of continuity, linearized equation of continuity. Replace this by ik, this by minus I omega, and solve this equation. So you will get an expression for perturbed beam density, and that turns out to be very similar to before, and the value is N1b is equal to minus N0b E k square phi upon m gamma 0 cube omega minus k V0b whole square. So mathematically there is only one change in the density perturbation due to relativistic effect, that the effective mass of the electron becomes rest mass multiplied by gamma 0 cube, and gamma 0, as I mentioned, is equal to 1 minus V0 b square by c square to the power minus half. And if you want to express this in terms of beam voltage, it turns out to be about 1 plus magnitude of electron charge into accelerating voltage of the gun upon m c square. So this is the voltage that you apply across the diode or the electron gun. So when you apply 1 million volt, this quantity becomes 2, gamma becomes 3. When you apply 500 kilovolt, then this ratio, this quantity is unity, gamma is equal to 2. So it depends on how much voltage you apply to the electron gun that is producing the electron beam. Gamma 0 can be controlled. So by gamma 0 increase in gamma 0, V0b increases, but V0b cannot increase beyond c. So the largest value V0b can take is c. Hence the phase velocity of plasma wave cannot exceed c if the wave is to be generated by an electron beam. Well, the plasma response is the same. You can deduce from here the perturbation caused in the plasma response, plasma electron response, whose electron density in equilibrium was N0, then E k square phi upon m. For the plasma electrons, they are not moving in the initial in equilibrium, their velocity was 0, so gamma 0 is unity, and V0b is 0, so this becomes omega square. You have to use this in the Poisson equation, which turns out to be equal to E upon epsilon 0, the free space permittivity, into N1b plus N1. Replace this del square by minus k square, and you get the dispersion relation. As before, the dispersion relation I will write down for the plasma wave is 1 minus omega p square by omega square is equal to beam plasma frequency square upon omega minus k V0b square multiplied by gamma 0 cube. You follow the same procedure as we followed for the true stream instability due to a non-relativistic electron beam to solve this equation. You write this equation as omega square minus omega p square multiplied by omega minus k V0b square is equal to omega pb square into omega square upon gamma 0 cube, and the growth rate that you obtain from here, just this factor is the additional factor. So what you get, omega we write as omega p plus delta, and choose omega p equal to k V0b. In this case, this equation gives you delta is equal to omega pb square into omega p upon 2 to the power 1/3, and for the unstable mode this into gamma 0 cube is there, multiplied by minus half plus I root 3 by 2. So the imaginary part of delta is the growth rate, which is down by the Lorentz factor. This is the main important effect of relativistic mass variation. So the growth rate is gamma, well, not this, this gamma is equal to root 3 by 2, and if I write in terms of beam density upon plasma density, then this is 1/3 into omega p, plasma frequency of the plasma electrons, and gamma 0 comes in there, gamma 0 of the beam. So this is the modifying factor for the growth rate. Well, now I would like to elaborate some of the applications of this study. Where are you really going to encounter relativistic electron beams? What are the use of those beams? Well, relativistic electron beams are employed in devices that produce coherent radiation, like free electron laser is a very common device. Actually, at one time relativistic electron beams were seen as a good candidate for thermonuclear fusion also, that you can have a pellet of deuterium tritium and you can bombard this by a electron beam, and then this beam can heat this pellet to fusion temperature and one can achieve nuclear reactions and nuclear energy. However, later on people found that this scheme is not that efficient because electrons are light in mass. So rather than using electron beam, people are employing ion beams. But there is something different. But electron beams are very commonly employed for generation of coherent radiation. Now the issue is that you have a gun that produces the diode that produces the electron beam, and this is the point where you have to deliver this beam. Suppose this is the structure where the radiation is to be generated. These two may not be same place. There may be finite distance between the two. So this is the electron gun. Electron beam is coming out from there, and this is the delivery point. So the distance between these two, if you launch a high current beam, then the beam will diverge because of electrostatic repulsion. Electrons are negatively charged entity, they will repel each other. So what has been found that if you have to transport a beam from a source to a delivery point, you must pass this through a plasma. What the plasma will do, if the plasma density is larger than the density of beam electrons, then as the beam enters here, the electrons of the plasma move out to create a space charge neutralized region. So what the plasma provides what we call as the space charge neutralization, because the plasma electrons move out. So the electron density of the beam plus electron density of the electrons, plasma electrons, is equal to ion density. So initially N0 is equal to N0I, but once the beam enters the plasma, this electron density of the plasma decreases such that this condition is satisfied. So through the region where the beam travels, in that region, this is the electron beam going in a plasma like this. So in the beam region, there is a space charge neutralization, and hence there is no repulsion of the electron beam. However, if the beam duration is longer than the growth period of the two stream instability, then this beam will give rise to generation of plasma waves, and that puts a serious restriction. So, if you want to transport a beam through a plasma, you must ensure that the beam duration is not too long, otherwise the beam will generate a plasma wave and that will trap the particles. The quality of the beam will be greatly deteriorated and lot of beam energy will go into the wave. So, that is to be avoided. So, you have to choose the beam pulse duration to be shorter than the growth period. Growth period of the plasma wave is inverse of growth time. So, what you require, the beam duration should be less than 1 upon gamma. This is the condition. So, in all transport channels, this is an important consideration. Another important area where electron beam, relativistic electron beam plasma interaction becomes important is the area of coherent radiation generation. As I just mentioned, actually the important area very similar to this is in the acceleration of electrons. Let us see what I mean by this. I will give you an example of a recent experiment. People consider a plasma, they launch an electron beam of typically so much length. This is the temporal length or spatial length of the beam. The beam is going like this. The beam that was chosen for this study was about 28 GeV, highly relativistic electron beam, was launched into a plasma. This is plasma. What was seen, this is the front of the beam, this is the tail of the beam. The beam electrons lost little bit of energy, but the tail electrons gained energy, and the tail electron gained energy typically from 28 GeV to about 33 GeV. So, this was the energy gain, that how these tail electrons here gained energy when they come out here. The total duration of this pulse was about 1 plasma period. In 1 plasma period is inverse of omega p. As a 2 pi upon omega p, where omega p is the plasma frequency of the plasma. So, when you choose a beam passing through a plasma of typically 1 plasma period, people found that a plasma wave was generated in the plasma. You can visualize the situation when the beam comes over here. When the beam comes over here, in the wake or behind its tail, the beam produces a plasma wave, something like this. In this region, the plasma wave generated, and this extends up to here actually. So, this plasma wave then traps the electrons and accelerates them, and this result was a landmark because this initiated a lot of particle in cell simulations and lot of studies of electron acceleration by plasma waves driven by a highly relativistic electron beam. Well, this is just to demonstrate that a plasma wave can accelerate electrons at a very fast rate. Total length of the plasma may be of the order of a centimeter or a few centimeters. And similarly, this scheme of electron acceleration caught a lot of attention, that you may generate a plasma wave not by essentially launching an electron beam, but by launching lasers. So, people are employing the similar scheme to generate a large amplitude plasma wave that can trap the electrons and accelerate them. Please note that an electron beam of such a high energy will produce a plasma wave of velocity very close to c. So, what you require for electron acceleration is a plasma wave of phase velocity close to c. then such plasma waves, we shall learn in subsequent lectures, can trap electrons and accelerate them to very high energies. So, this is a very major application of electron beams, relativistic electron beams, to produce large amplitude plasma waves, and then those waves are employed for various applications. Well, in this context, I would like to mention one thing. Whenever a beam has to travel through a plasma, the beam does two things. Suppose I am launching an electron beam in a plasma, this is my electron beam. If the beam travels with under space charge neutralization, then there is no electric field seen by the electrons. So, their divergence is stopped. But when the beam travels, it carries a current, because beam essentially is an entity that carries current. With the move, particles move. So, if I consider a beam of density n0b and velocity v0b going in this direction, this will produce a magnetic field. You can easily calculate the value of magnetic field, and that will be in the phi direction, azimuthal direction, phi direction, and its value will be typically equal to, let me just write the expression. It turns out to be minus mu 0 n0 e upon 2 v0 b into r. What is the consequence of this magnetic field? The electrons which are at the periphery, these electrons under the Lorentz force tend a tendency to come down, and they may even get, they go like this. So, when the electron from the periphery goes to the axial region, its axial velocity slows down and it may even come back. So, the beams cannot carry too much current. The maximum current an electron beam can carry is of this order, otherwise it will turn around, because its self magnetic field is equal to m c cube upon E multiplied by gamma. E is the magnitude of electron charge, m is the rest mass of the electron, c is the velocity of light in free space, and gamma is the Lorentz factor of the beam, which I am calling gamma 0b. So, if you want larger current to be flown, you must choose beam with larger and larger Lorentz factor, larger energy. This is the important thing I wanted to mention to you. And before I close, a classic application of beam plasma interaction is in the understanding of a phenomenon called Landau damping. Let me say a few words about Landau damping. We have learnt that a beam can give energy to the wave whenever the beam velocity is greater than the phase velocity of the wave, or omega by k, slightly greater than this. Now, suppose I have a plasma which is Maxwellian, which has Maxwellian velocity distribution function. Suppose a plasma is in thermal equilibrium, there is no beam. What you can do, suppose there is a plasma field somewhere, and if I plot the distribution function as a function of Vz, the distribution function for a Maxwellian plasma is of this form. So, there is a plasma here which has electrons of very different thermal velocities, they are moving all around. Some of the electrons will be moving in the direction of the wave. So, I am considering the propagation of wave in the z direction. Then some of the electrons will be moving with the wave, and the ones which are moving with the wave with a velocity close to omega by k will be resonantly interacting. So, suppose the wave velocity is omega by k, I write omega by k here, then this is the electrons in this neighborhood of omega by k that are really resonantly interacting with the wave. They can be in Cherenkov resonance with the wave and can efficiently give energy to the wave or take energy from the wave. Now, what you see from the slope of the distribution function, that the electrons of lower velocity are more and higher velocity are less, because the slope of f with velocity is negative. Means if there are many electrons which are moving all around, the ones which are moving with the wave slightly with a larger velocity than the wave phase velocity, their number is less, and the ones which are moving slightly slower than the wave, their number is more. Then these electrons which are moving with a larger velocity will give energy to the wave. The electrons which are moving slowly, they will take energy from the wave. So here what you are getting is slower electrons are more in number is more than the faster electron number. What is going to happen because of this? More electrons are there to take energy from the wave, fewer electrons are there to give energy to the wave, and there is a net energy transfer from the wave to the particles. Net energy transfer from the wave to the electrons. This phenomenon is known as Landau damping, and this is one of the major phenomenon observed in plasmas. It is a very important process that gives rise to heating, efficient heating of plasmas, and I think we have to develop a kinetic theory to discuss this phenomenon at depth, and that we shall take some time. And with this we close our discussion today. Thank you.